Hi guys, my name is Sourav Chakraborty. I am a software developer in the GPU group at AMD, and I work on the for improving ROCm support in UCX. So today's talk is to share some status updates on the ROCm stack in UCX, how we have improved uh, over the last year or so, and it's not like just a list of changes. The goal here is to share some interesting insights that we came across as we developed these solutions. So as you can see, we have added quite a number of improvements in the ROCm support over the last year or so. But you can find all of these from the change log. So instead of looking into this, let's start with one of them. So, so this one is a straightforward one. We added ROCm memory support for the perf tools in UCX perf tools. So now you can measure the performance of D2D transfers with ROCm GPUs. And we also added support for D2H and H2D transfers. So I'll be using these terms like D2H and H2D quite a bit. So just to make sure that we're on the same page. So D2D is device to device or GPU to GPU. D2H is device to host or GPU to CPU, and H2D is CPU to GPU. Um, Yeah, and so one of the big changes that we made was removing dependency on GDRCopy. So earlier we had a ROCm GDR module similar to the CUDA GDR transport that used the GDRCopy library. So the goal of that was to uh, allow the CPU to access GPU memory in a fast way. But all the AMD ROCm GPUs have large bar support that allows the CPU to access the GPU memory directly without going through the GDR module. So we were able to remove the dependency on that. And as as the earlier talk from Jamin showed that a lot of users had issues building and linking with the GDRCopy module. So I think, so we think this is a good improvement. And now the ROCm copy module itself has the functionality required to support fast uh, support the ROCm features that ROCm GDR was providing. And the good thing is that there was no performance degradation from that. In fact, we improved performance a little bit. So if you look here, this is device to device latency within the same node and the bandwidth. So this is between two GPUs. And as you can see earlier, so the ROCm copy performance is quite poor, used to be quite poor compared to ROCm GDR. And that's why the GDRCopy module was useful. But now ROCm copy performs similar or better than the ROCm GDR module. So we no longer have to rely on the ROCm GDR module. And same for bandwidth, we have a similar performance or and a smoother curve. So how this was actually done was based on um, SSE-based memcpy for small messages. So we did some investigation to see. So we found that the glibc-based memcpy that comes with comes with the system installations is very slow when it tries to do device to host transfers. The reason is that reading from the GPU is slow using regular uh, move intrinsics that the memcpy uses. So we did a exhaustive study of different vectorized copy intrinsics like AVX, different versions of SSE from SSE 1 to all the way to SSE 4.1. And we tried to compare which one performs the best for these device to host transfers. So we found that using vectorized copies is helpful, but what is also helpful is using something called non-temporal instructions. So this is a type of read from the uh, from the memory that does not modify the cache. So the details are in the pull request, but basically using that special instruction allowed us to write a very fast memcpy that performs like 50 times faster when doing D to H transfers. And so that's the one that we are currently using in the ROCm copy path. So here are some numbers that we can see from using this memcpy. So as you can see, we have a very big improvement in terms of latency and as well as bandwidth. So one of the limitations of this is that since it uses this AVX or SSE instructions, uh, it's only available if you build your own UCX with enable optimizations or the configure opt uh, uh, this particular configure a command. But in the configure release version, that optimizations are not enabled because those are meant for wider distribution where machines may not have the necessary AVX or SSE instructions that are required. So what we would ideally like to do is have some sort of way to enable this at runtime if the system has SSE support, and if not, it will fall back to the old regular memcpy. So this is something that we would like to see from the. So this will require some changes in the uh, build build and configure steps. So we'd like to see some feedback from the community on how to do that. Okay, so let's now move on to another one. So this one is improved agent selection for IPC transfers. So as we know, IPC is used for large GPU to GPU transfers within the same node. So let's say we have uh, so the two GPUs within the same node, and we are trying to move some data from GPU 0 to GPU 1. So there are actually two ways we can go about this. GPU 0 can, the source GPU can write the data to the remote destination GPU, or the destination GPU can read the data from the source GPU. So there are these two terms that we sometimes use: local read, remote write, and remote read, local write. But they are like very hard to pronounce, so I will just call them write and read. So one interesting trend that we see is that there is a big performance difference between these two methods, which can be slightly unexpected. So over PCI, we see that the write is much faster than the read. So write actually achieves what is the close to the PCI theoretical limit. So it writes at around 27 gigabytes per second, whereas the read only achieves only around 7.5 gigabytes per second. So this is actually not because of the AMD GPUs per se. This is more this limitation comes more from the PCIe side, and so the root cause of the difference is how write and read transactions are treated by PCIe. And for PCIe, there are only a certain number of outstanding reads that are allowed to be there. So that kind of limits the read performance over PCIe. And this is also only applicable to PCIe systems. So if GPUs are connected through something like NVLink or AMD's Infinity Fabric or XGMI, they do not show this problem. In those cases, they are able to saturate the link bandwidth. So this is specific to PCIe systems. Now, the impact of this difference is that the default get zcopy approach, which is default in UCX for IPC transfer, performs quite worse than put zcopy, because get zcopy uses the read path where the destination GPU is reading, and the put zcopy will use the write path where the source GPU is writing. So what is the way around that? Can we make get zcopy better somehow and go from here to here? So we actually do have a solution for in the ROCm IPC module. So instead of using the heap memcpy, which is the equivalent of CUDA memcpy, we can use the driver layer to tell the source GPU to write the data to the destination GPU. Basically simulate put zcopy from within the get zcopy. So use the write functionality even if we are using get zcopy. And with that, we actually do see significant improvement in performance. We go from 3 to 4 gigabytes per second to 22 gigabytes per second. I'm not entirely sure why it doesn't reach the full 27 gigabytes per second. We are looking into that, but I believe that has something to do with the extra overhead of telling the other GPU to do our own stuff. But this is still acceptable. But the main limitation of this approach is that the remote GPU has to be visible to the so both the GPUs has to be visible to both the processes. So if we go back to this slide here, so let's say process 0 has owns the GPU 0 and does not cannot see the GPU 1, and process 1 has the GPU 1 and cannot see the GPU 0. In that case, we cannot use that approach, right? Because we cannot, there is no way to tell GPU 0 to write the data to us if we don't know that it exists, or if we have no way to send the command to that. And we have seen that actually quite a number of applications uses these heap visible devices, which is equivalent of CUDA visible devices, to limit the visibility of GPUs to each process, individual processes. So each process kind of only sees the GPU it has been allocated and does not have visibility to other GPUs. So we cannot use this approach reliably unless we know that these heap visible devices or the CUDA visible devices is not being used by the application. So, so we would like to think of some solution for that. One way would be to make this approach default and let the users specify some environment variable that they are using these visible devices to limit the visibility, in which case we can fall back to the regular get zcopy at the cost of performance loss. Or one solution could be to use put zcopy by default instead of get zcopy if we detect that the system has PCIe instead of something like NVLink or AMD Infinity Fabric, which does not show this problem. So this is also kind of an open question, and we would like some community feedback on that.
Just a comment here. So I wanted to ask Yossi if, it seems like depending on the vendor, it could be useful to have a way to allow for you to specify your own protocol configuration. Yesterday, Yossi talked about protocols V2, where some things are decided based on certain characteristics of say iFace attributes, for instance. But I wonder if it's also useful to have some configurability in terms of what the vendor thinks is most useful, is the most useful protocol, and if that sort of flexibility should be provided in UCP as well.
So in this case, what is the reason this is better than the other?
Sorry. Specific. Which one is better than what?
Can you hear me?
Yeah.
Yes.
So what is the basic reason here that we need a different way to select? Is it just because of topology?
Yeah, it's like a mix of topology and how the system works. So basically, PCIe write performance is always better than PCIe read performance. That is true for up to PCIe 4 at least. So put zcopy will always win compared to get zcopy on these kind of systems.
Yes, so I think it's part of the item we discussed that we need to make protocol estimations, performance estimations of iFace per operation rather than one for both put and get. Do you think it will cover this case?
Yeah, so only thing is that it's not a property of the IF, just the IF interface. It's also a property of the topology. And so by topology, I include what is the type of link between two GPUs. And it could kind of vary because the same system can have, let's say, some GPUs which are connected through NVLink and some GPUs which are connected through PCIe. So it will have to be between two peers. Different protocols will do better.
So I think it's in different places because in case of the NVLink, for example, then it's the responsible of the IPC transport to report the bandwidth, assuming that the memory that it transfers is as close as possible to the agents which are doing the transfer. For example, we obviously don't assume that there would be some kind of DMA between one GPU to the other GPU in case of IPC, right? So we can assume like the optimal locality there, and we can add to this, or actually not add, but combine this with the topology bandwidth. And like Akshay said yesterday, the topology bandwidth should also depend on the operation type. And if we do the minimal bandwidth between the best which transport reports for that operation, along with the what the bandwidth which topology reports, maybe it could be enough to reflect the actual bandwidth we expect.
To me, that makes sense.
Go ahead, Akshay.
So I was also going to say that one of the drawbacks with reporting CUDA IPC bandwidth today is that we can state upfront what is the potential optimal bandwidth, but it could be the case that when it comes to the time of the transfer, how we do it in CUDA IPC is that we try and exchange a memory handle, at which point we'll find out, okay, we can't really exchange, so we may need to resort to some other protocol. And even when we exchange, we don't know for a fact if it's going to go over NVLink or PCIe. So one of the drawbacks there is, at least we don't yet have the API in CUDA IPC transport to detect upfront whether NVLinks or PCIe will be used between a pair of devices. And on top of that, just the fact that we have both capabilities, it's only at the time of transfer we'll be able to find out if we can use CUDA IPC. So there's this one drawback, and I don't know if potentially introducing, we have NVML to potentially find out, but it does complicate how we estimate IFAS attributes, and it may require that we change IFAS attributes dynamically. So I don't know if UCP allows for that yet. Like UCP expects IFAS attributes to be static, right? You say it up front, and on those decisions, we'll make some decisions later, which the protocols will pick up.
I think one problem here is that whenever we represent GPUs, we only have a single UCT device, which actually represents multiple different GPUs. And UCP cannot capture the information that this buffer resides on that GPU or that device, and the other is on some other device, and maybe they are connected with some fast interconnect, or maybe they are not. So we need some way to distinguish maybe on which GPU each buffer is located, and then use the topology somehow to determine.
That seems like the best way to represent what's happening in hardware. I mean, we do something that's specific to GPUs, or individual GPUs, as opposed to treating all GPUs as one memory domain.
And I guess that GPU transports should be able to detect which GPU is it, right?
Yeah, I mean, CUDA certainly has the API to figure out if I have a context running, which GPU is it, what is the ordinal associated with the GPU. And based on that, it's possible to associate IFAS attributes. And based on that, with the addition of more API, like there's NVML API, which allows you to potentially figure out, what are the NVLink connected GPUs to the current GPU. I don't know if something equivalent exists for ROCm, and I have to, I actually go back and check if that's in fact very true, to see if NVML is flexible enough to let you know what are all the endpoints and what are the transports, the interfaces for those endpoints. So that's open.
Maybe if we could, even without changing so much, use the sys device index. So each individual GPU would have different system device, like a different memory unit. and then the GPU transport would detect the sys device for every different GPU, and the query function, the performance query function, would have to take two parameters, like the source device and destination device.
That makes sense, but which performance query function are you referring to here?
So, for example, CUDA IPC performance could take two system device indexes and maybe the operation, so it could tell which direction the memory goes, and then it can detect probably if they are connected through NVLink or not, and if not, for example, it could resort to topology a query distance, and if they are, then it's according to NVLink speed.
That makes sense.
Yeah, I think that is reasonable because so if we have n GPUs on the system, we ultimately need a way to uh, get the information about n. So there will be an n square matrix, right, with of read and write speeds between them. So there has to be some way to export that information to UCX so that it can make the decisions based on that.
So Yossi, just going back to my original question, right? So one of the differences, I mean, why I talked about configurability of UCP protocols V2 is because I'm hypothetically there could be a situation somewhere down the line where we see that what we have composed for CUDA GPUs may not be consistent with what is the case for ROCm GPUs. So I was just hinting towards whether it makes sense to have protocols based on what the vendor prefers, and this is something that can that the vendor populates. But I think what you're saying is if it's intrinsically a property of say PCIe, then we don't have to do something vendor specific. But my only question is, are there some situations where it does make sense to have vendor specific protocols?
So we can divide this to two questions. One is whether the current problem that Sourav just presented is vendor intrinsic or not, and we can solve it in some vendor independent way. And the second question, whether down the road, if we have something which is not vendor intrinsic, or at least not that easy to make generic in a short time frame, how can we force specific things? So for the first question, as far as I could tell for now, seems like it's not really vendor intrinsic because we need to extend the performance query API basically to accept the system device of both source and destination. And regarding the second question, so we can. So yesterday, Maju suggested that we can have some set of configuration parameters to fine-tune protocols. And we're also looking into adding configuration file into UCX. So we can potentially add some vendor-specific configuration files, which, for example, for essentially for every member of the community or whoever, for best configuration for each type of system, type of vendor, or whatnot.
Sure. Okay.
Okay, so I think we are running out of time, so I will move on. So the next improvement is D2D transfers for internode using GPU Direct RDMA. So I'll just give some background. So we can, if we are trying to transfer some data from GPU 0 to GPU 1, the NIC can read it, send it over to this NIC, and then it can write to the GPU 1. So this is the default GPU Direct RDMA path. The problem with that is if we are using GDR writes are much faster than GDR reads for the same PCIe limitations as before, and there is no way to avoid it in this case because all NICs are connecting to the PCIe interface, so there is no NVLink or Infinity Fabric to connect them together. So that's why we have the same 7.5 gigabyte per second limitation here. And so this means that, and this also depends on how the how close the GPU sits to the NIC. If it sits in the same root complex, we do get slightly better performance. If it is on the different PCI root complex, this is the performance that we are limited to. And also, we cannot switch to put zcopy here because even if we use put zcopy, this the path is the exact same here, and this read path is the bottleneck from GPU to the NIC. Uh, so the solution to that is using staged device-to-device transfers for internode, where we stage the GPU buffer on the CPU memory, and then the NIC reads from there. And since the NIC can read from CPU memory, uh, and this bottleneck, the GPU to NIC bottleneck does not exist here. So this actually gets us good performance. So one limitation here is that the GPU, this transfer from GPU to CPU or the staging path must be done by the GPU for it to be performant, because it's the as we saw earlier, the CPU is not very good at reading GPU memory in a very high performance way. So this is not actually something that we did on our own. Devender added this support for NVIDIA GPUs initially. And so we have added support for ROCm GPUs as well. So that is in a pending pull request. That should be merged soon. So the challenge and the slight difference from how it is done for NVIDIA GPUs with ROCm is that instead of using CUDA memcpy to do this staging path, we use HSA copy, which is equivalent to the driver-based copies for CUDA. And this requires the host memory to be registered by the GPU in the ROCm copy module. And that has some interesting side effects and requires some changes that needs to be addressed. So with that changes, we actually see a very good improvement in performance. So as we can see with in terms of latency, we see a 3x improvement from using GPU direct RDMA, the current design, to the stage design. And we also see good improvement in the bandwidth. So we go from the 7.5 gigabytes per second to up to 21 gigabytes per second, so close to the line rate. Of course, there is some overhead due to the pipelining and staging involved, so it does not reach the full 24 gigabyte per second. So there are some. So I'll conclude with what's next in our roadmap. So we have now support for MPICH. Earlier we only was supporting OpenMPI. Although to be honest, it's not. There is not a lot of effort that we had to put in here, because MPICH already has UCX support, and the UCX is doing the bulk of the heavy lifting for us. So thanks to the UCX community for that. And we also have a few other things that we are working on, but unfortunately I didn't get the permission to share them here. So I guess we'll try to share them as they're made public. And what we are looking forward to from the community is mostly on the topology side. So how to detect and how we can detect and encode these different types of links. So as systems become more and more complicated with larger number of GPUs and different types of links, then it needs to be more flexible to handle that. And also how we can encode distance between different PCIe devices. So for example, this scenario, so this scenario's performance depends on where the GPU sits relative to the NIC, and the performance actually varies significantly based on that. So there needs to be some way to define those distances and use that for the UCX decision-making process. So thanks. This is just some standard disclaimer. And yeah, I would like to address any questions that you have.